We will discuss Doppler effect in this lesson, and we will see that how it affects waves. Now, Doppler effect is observed in stationary waves. It is observed in uh, sound waves, light waves, and most of the waves that we're generally familiar with. It is observed in that. So first, let's learn what is Doppler effect. Now, Doppler says, or the scientist who actually discovered this, he observed that if, let's say, the observer is stationary, we will hear a certain frequency. So we will say that this is F heard or F perceived. What he thinks is actually the frequency. And this is not only just the perception of the observer, this actually is measured on the CRO with the help of a mic, and we can see that very clearly, that there is a change in frequency. Now what happens, that for the sake of understanding, let's say that the standard frequency of the emitted sound is 500 hertz, and the velocity of sound in air is 330 meters per second. For the sake of this example, let's say if we had an ambulance or a car that has a horn, and this horn is making a sound of 500 hertz. And if this car is moving towards the observer with a velocity v, for example, let's say we keep this velocity v fixed as 35 meters per second, then what happens is that the actual frequency heard by this person while it is moving towards the observer is actually a bit higher. We will calculate this later, but for this example, let's assume that that increase in frequency or increase in the perceived frequency, let's say for the sake of example, comes out as 525 hertz. Now the actual frequency produced by the sound wave is 500 by the source. But why this person is hearing the frequency a bit higher? Now we'll get to that later. So when this object or this sound producing, let's say van, moves away from the observer, then this heard frequency and the perceived frequency actually is less than the actual value. So for the sake of this example, let's assume that it comes out as 470 hertz. Now the velocity has not changed. It is still the same. It is 35 meters per second in both scenarios. It can change, it doesn't matter, but the point of the matter is that the frequency is changing by the person who is observing this, which is quite odd for any sound wave to change frequency midway. It's not possible, but we can see that it is perceived and it is being observed. So let's try to see what's actually happening with the sound's wavefronts. Now we know wavefronts are actually the areas which have the same amplitude, and when they're connected to a single line, that single line comes out as a wavefront. Okay, so let's see what's actually happening with the wavefronts. Let's see an animation. Okay, so in this animation, what we are going to observe is that this black dot is actually the sound producing source. This is where the sound is actually coming from. Okay, and this is the observer, the person who's actually observing the sound. Okay, so we're going to see what happens with the wavefronts as the animation progresses. Okay, so let's try to see what's actually happening. So we let this animation to play. Now this is producing a sound already. Now notice that the original position of this person or this object was somewhere along this line. This was actually pointed at this location. And as soon as it started moving towards this side with a certain velocity, we can see what's happening with the wavefronts. Now, ideally speaking, the wavefront should not have changed, but what's happening is that this sound wave is moving at a speed of 330 meters per second, the wavefront. But as the object is also moving, the wavefront that is actually behind the other sound, behind the first wavefront, has actually moved a certain distance because this source was also moving. That is, although this is moving at 330 meters per second, but since the source is moving, this wavefront has actually moved a bit further than it actually should have. It's like a person throwing a ball at a certain speed, but if the same person throws a ball while running, then that speed will be a bit different than this one. So that's just a simple visualization how to visualize this. So what's happening in this situation is that the wavefronts are actually shrinking together, right? So what's happening to the wavefronts? Let's see what's happening to them. So I realized that this is the wavefront and this is another wavefront. So the distance between them is the wavelength. We know that from waves, v is equal to f lambda. And if speed is constant, which I told you that the speed of both wavefronts is actually exactly the same. If that is the same speed, then that means that we can follow a relationship between this. We can bring lambda over there, and we can see that f is inversely proportional to lambda. And in this case, when the object is moving towards the source, we can see that the lambda is decreasing. So what happens? The frequency increases because this is an inverse relationship, right? That is why the perceived frequency or the heard frequency by the person actually increases slightly, because the wavefronts are shrinking together. If the wavelengths are shrinking together, wavefronts are shrinking together, the wavelength appears to be decreasing and the frequency will appear to be increasing. Now, on the other hand, if we let this animation to run and see what happens on the other side, let's see what happens if we let this run. Now, we will allow this object to cross the observer and see what happens. So it is still moving towards them. Now it crosses away from the observer, and let's pause this video at this moment and discuss the new situation. Now see that this person and this object is actually moving away. Now the object is moving away. So what type of wavefront are actually reaching the observer? The observer experiences a wavelength that is actually this much. Now we just proved that frequency is inversely proportional to wavelength. We have seen that in comparison to this situation, this lambda 2, and let's call this lambda 1, lambda 2 is much greater than lambda 1. So if lambda has increased, most definitely frequency would have decreased. So as the observer is moving away, as in this case, the heard frequency by the observer at this location would decrease, would fall down. This is exactly what I've discussed at the beginning of the lesson, that when the object is moving close to you, the frequency that you might hear, let's say, is 525 hertz. But as it is moving away, it's possible that the frequency that you hear is, let's say, 480 hertz, all because of the Doppler effect. And what is the Doppler effect? It's the shrinking of these wavelengths together while the sound producer, the source of the sound, is moving. I hope that this visualization helps us to understand why the wavelength is changing. I'm going to move back to the lesson now. Okay, so this is what we discussed, and we saw an animation for that as well. Let's write down a formula for this. So what happens if the object is moving towards the observer? Okay, so we write down that source is moving towards observer. And then we have the source moving away from the observer. Okay, let's write down the formula. So what is F? F is what is being perceived, what is being heard. So let's call this F equals to F naught. Now, what is F naught? F naught is the standard frequency that the speaker was actually producing. So F naught is the standard frequency, and it is being multiplied by the speed of sound divided by the speed of sound minus the speed of the car or the object itself. Over here, the formula changes a bit. So F, what is being heard, F naught standard frequency, and then a speed of sound divided by a speed of sound plus the speed of object that is carrying the sound, that is the source of the sound. Okay, so let's write down the key. We have F in both equations as what is being heard or perceived. F naught is the actual frequency, what the speaker is producing. Vs is the speed of sound or the wavefront. In case of light, this wavefront that we've just discussed, this wavefront will be moving at a speed of the speed of light. Okay, all right. So then we have V as the speed of the source or the object that is carrying the speaker in all of these examples. Now let's apply this formula in this situation and let's see what happens. So it says that an ambulance is moving along and the speed of sound and the speed of the ambulance is 30 meters per second. The speed of sound is 340 and the actual frequency it produces is 2000. He says what's going to be the frequency when it is moving towards the man and when it is moving away from the man. First thing, we should memorize that if this is the observer and if this is the ambulance, If the ambulance is moving towards the observer, then the frequency should be greater than 2000. So 18, 20, and 8 foot should not have been the answers, or could not have been the answers. So we're going to eliminate option A and B straight away. It's not going to be our answer. And if the ambulance is moving away, then the frequency heard will be a bit lower. So in option A and B, they have written the answers opposite way. Okay, let's try to calculate this. So while it is moving towards the observer, and we are going to use these formulas most definitely, right? So what do we get is, and the standard frequency is 2000. This is what's going to change. So F while coming towards, so this will be 2000 multiplied by 340 meters per second, which was given in the question, divided by 340 minus 30. And if you calculate this, your answer is going to be 2193. This will be 2193 hertz. Now, if you are moving away from the observer, the frequency falls, and you can notice over here that the standard frequency was 2000, but what is being heard? Slightly higher frequency because the source is moving. So over here we have 2000, then 340 divided by 340 plus 30. Again, I'm choosing the formulas from this position. And in your syllabus, some student might ask, in your syllabus, there's only one possibility: when the source of sound is moving and the observer is stationary. So it's the other way around as well, but that's not a part of the course. So if you solve this answer, you're going to get 1838 hertz. Now we can notice that the only example that represents these two numbers, 2193 and 1830, which is rounded off to 1840, and this has been rounded off to 2190, is option D. Move to this question. It is exactly the same question, but a bit of a twist. Over here, you'll have to perform a bit more calculations. So let's see what we have to do over here. He says that the speed of the train, let's say, is, or a car is 30, speed of sound is 336, and the standard frequency is 400 hertz. It's generally given. He says, what's the change in frequency? Now, please notice, the change is never linear. You can notice in this question as well that from 2000, the value has changed to 2193. So it's a delta or a change of 193. Don't expect that this will also be a change of 193. Please, this is a mathematical issue. These are not proportional changes. So please calculate these values on your own before doing this blunder. Okay. All right. So let's move to this position as well. So we're going to calculate both of them. So let's calculate why it is moving towards and when it is moving away from the observer. So towards, it's going to be the standard frequency 400 hertz, 336 speed of sound divided by 336 minus 30, which was the speed of the object. And then when it's moving away, we'll have 400 standard frequency, then 336 divided by 336 plus the speed of 30. So when you solve both of them, the answer that you're going to get is, for the first one, you'll get 439. So this is 439 hertz, and this will be 367 hertz. So you found the frequency in both situations, right? If you were to visualize it over here, what's actually happening is that at this position, the frequency has been found as 367 hertz. And at this location, it has been found as 439 hertz. Because the waves are congested together, over here they are spread out. So frequency decreases, and over here frequency increases. Right? So just another visualization for this one. Now he's asking us about the delta or the change. What we're going to simply do is find the change in frequency. So 439 minus 367, we get 72 answer as our answer. Now, what some students generally do is, since we are supposed to find out the difference, what they generally do is do this question directly. So what they do is 336 divided by 336 minus 30 minus 336 over 336 plus 30, and then multiply this with 400. What they do is take the 400 out of both equation common and then solve this fraction, and they directly get 72. You can try this on the calculator as well. In this question, we'll realize that Doppler effect is not only for sound waves, it's also acceptable for water waves. It's also acceptable for these light waves as well. So what's happening in this situation, that an observer on Earth is experiencing that a frequency of the star is changing. So what's happening is that if the star is rotating like this, then at this moment in time, it is moving towards you. So the perceived frequency should be higher. And at this moment in time, it's moving away from you. So the perceived frequency should be lower. This is what he has shown in this graph, is that the frequency is sometimes higher, sometimes it's lower. And based on that period, we can also, of course, predict the radius of the orbit, but that's not a part of this course right now. So he asks you that if the binary star speed increases, for example, if it starts rotating at a higher speed, what's going to happen to this frequency, which was already the maximum value? And what's going to happen to this frequency, which is already the minimum value? What will happen to them? Now, this is a mathematics problem. So for that, we are going to make a small table over here, which you can try on your own as well. If we were going to do this numerical with reference to light, then please be advised that if the formula was going to be like this, f naught standard frequency, then it would have been 3 into 10 raised to power 8 divided by 3 into 10 raised to power 8 minus or plus v or the velocity of the star. Now, I've tested this method and this actually proves the problem. The problem is that these values are too large. So even if you add or subtract a value, they don't give you a meaningful change. So for the sake of example only, although if it was light, I would have done this, but for the sake of example only, I'm going to choose this as an example of sound so that we can see the mathematical differences happening over here. So I'm going to choose the speed of sound as 330, and I'm going to choose a standard frequency as 500 Hertz in all the examples. What I'm going to do in this question to show you the mathematics of this is to calculate at different speeds what's going to happen. So let's say that the speed of the star is at some instant in meters per second. Let's say at one instant it is 20 meters per second, then at another it is not 30 but 40. Let's double this so we can see the effect. And at one instant it is 100. Okay, so I'm going to try 3 examples. So in 3 examples, we're going to see what's going to happen to the frequency while it is moving away or if it is moving towards us. So this is the frequency when it is moving away from us. And this is the frequency when it is moving towards us. And I can expect that over here the frequency increases, and over here the frequency decreases. So I'm going to solve this one example for you so you can put in the rest of the values. So this will be, and the standard frequency is 500. So this will be actually calculated 500 into 330 divided by 330 minus x. Now this is that x that you're going to put in all 3 situations. And over here, this is also x. So in this situation, this will be 500 into 330 divided by 330 plus x. Sorry, I've written this in the opposite way. This will be like this. So while it's moving away, this will be plus. When it's moving towards, it will be minus. So when you put in these values, you'll find out that this is, you can try this on the calculator as well. You will find out that this will be 532. This comes out as 568. This comes out as 770. Over here, you find out the values as 471. This is 445. This is 383. Now notice what is happening. As you increase the speed, you are increasing from 20 to 40 to 100. The frequency that was supposed to drop down, or the frequency that is supposed to be less, is decreasing even more. It has already reduced from 500 standard frequency to 471, but if you're moving faster, then it is going to reduce even more. If you're moving faster still, it's going to reduce even more. So for the minimum frequency, I feel that it's going to decrease even more than before. And what's happening to the increased frequency when it is moving towards you? So first, it increased from 500 to 532, and when you double the speed, it actually goes to 568. And when you have increased the speed to at least, let's say, 5 times of 20, the frequency goes up to 717 Hertz. So the frequency is increasing if you increase the speed. So I believe that the frequency is increasing. If the speed is increased, the change is larger, and that is all down to this mathematics format. This is not a problem for physics. This is actually a mathematics understanding, right? So if you increase the difference, if you increase the speed, this difference, this delta increases or decreases, and if it gets multiplied with 500, it will produce lesser and lesser or larger examples respectively as compared to away and towards course. So in my understanding, this is going to be option C. A small tidbit before we end the lesson. What's happening with the jet fighters? What's actually happening with their sound barriers or sound wavefronts? So if we go to this position, I'm just going to show you the animation of a jet fighter. What's actually happening in that case? How the Doppler effect actually plays in that. So in the jet fighter, it is moving even faster than the speed of sound. So the wavefronts actually lag behind the jet fighter. You can see this in the animation. I'm going to play this and see what's happening. So you can see that the jet fighter is leading because it's moving much faster than the speed of sound, and it is leaving the wavefronts behind, even the ones that are compressed and even the ones that are actually behind it. So, and that speed, for the sake of interest, is called Mach 1, Mach 2, and Mach 3. So if the speed of the jet fighter is, let's say, a multiple of 1 times the speed of sound, then that is called Mach 1. If the speed of jet fighter is actually 2 times the speed of sound, it is called Mach 2. And right now we can see what's actually happening. The jet fighter is moving, let's say for the sake of understanding, at 500 meters per second, and these sound wavefronts are actually moving at 340 or 330. They can't keep up. So in that situation, the wavefronts will look something like this. Okay, I hope that this is all for this lesson. I hope that we've understood what we came for.